Hi, I'm Haley Cole from the Department of Physics at Colorado School of Mines, and today I'd like to talk about quantum entangled breathers and Goldilocks quantum cellular automata. To begin, I'd like to define complexity. Complexity characterizes a system of multiple individuals which may interact in many ways, resulting in collective group behaviors. Two aspects of complexity I will touch on today are persistent emergent phenomena, which we see as robustness, and connectivity. To start defining just what quantum entangled breathers or QEBs are, we need to define three things, starting with elementary cellular automata. Elementary cellular automata have two states, 0 or 1. These states form a lattice and interact by a rule that states if the site to the left and right and the site itself is a certain pattern, it will always evolve to a 0 or 1 according to the rule number. The connectivity leads to emergent phenomena seen in group behavior. You can see how the complexity of the system evolves as time continues. So as you can imagine, quantum cellular automata also have states, but this time it is not either 0 or 1, the states are qubits. These evolve by a local unitary operator with the same rule conditions as elementary cellular automata, dependent on the neighbors of the site. Although now we consider a neighborhood to be 5 sites, or 2 neighbors to the left and 2 neighbors to the right, this also leads to emergent group behavior marked with complexity. It is clear to see that both elementary cellular automata and quantum cellular automata exhibit complexity. As I define complexity, it's a system of multiple individuals, these would be the states, that interact in many ways. The interactions are the local unitary operator as well as the neighborhood operator, and these result in collective group behaviors, seen as the image on the right-hand side of the screen. The final piece in defining QEBs is breathers. Breathers are a solution to the nonlinear Schrödinger equation, which are also called excited bright solitons. These are highly entangled, allowing for us to call them complex because of the connectivity of the system. From the graphic, you can see the breathing pattern that gives its namesake. Discrete breathers exhibit famous robustness and complexity we hope to see in QEBs. QEBs are a mix of discrete breathers and quantum cellular automata in continuous time. They use the Hamiltonian of quantum cellular automata but show the emergent dynamical structure of the breather. The Hamiltonian used to define the QEBs has two parts. The first is a local unitary operator that flips the state from 0 to 1 or 1 to 0. The second part is the rule, which activates the local unitary operator if the right number of neighbors are in the spin-up state. We use Goldilocks rule sets, which are 2, 4, 6, 12, and 14, because they exhibit just the right amount of activity, but not too much. Here's an example of Rule 4, which evolves if 2 of the 4 nearest neighbors are spin up. You can clearly see the breathing pattern as the 2 sites left and right of the middle blink from spin up to an entangled state, and the states to the side of those middle sites go from an entangled state to spin down in an oscillating breathing pattern. So, how do we test if QEBs exhibit the same complexity as discrete breathers? We test their robustness because if the system is robust, we have persistent emergent phenomena, one of our aspects of complexity. So therefore, we are going to add noise or unwanted disturbances to the system and see how our emergent phenomena persist. The first test is to perturb the initial condition. We did this by adding uniform spatial noise, or adding a fraction of bosons to each site in the lattice, where 2% noise corresponds to 0.02 bosons on each site. The left figure is 2% noise, which keeps the emergent phenomena intact. We finally see breakdown of the system at 50% noise, shown on the right. This makes intuitive sense because at 50% noise, the middle site no longer has 2 spin-up neighbors, which was the condition for Rule 4 to enact. The second test is to perturb the Hamiltonian. We did this by mixing rule sets and then calculating the lifetime of the QEB. This was done by computing the 2-point correlator and combing the frequencies for the first local minimum. The time to the minimum is the lifetime of the QEB. We conducted these tests on much larger timescales and found a faster rate of decay of lifetime. At a rule error of 0.33% and Hamiltonian perturbation of 1.2% noise, we find a lifetime of 13.5% of the original lifetime, with the unchanged QEB on the left and the perturbation one on the right. At 8% Hamiltonian perturbation noise, the lifetime has decreased to 3.4% of the original lifetime, although the QEB still persists to 100 time steps at this noise level. Furthermore, you can still see a ghost of the blinking pattern even after we say the QEB has died. I'd also like to note that the breathing pattern is not as clear in this time resolution due to the fact that it repeats about every 5 time steps. Future work would include uniform spectral noise, which would involve taking the Fourier transform of the initial condition and then adding a set frequency to all the components and taking the inverse Fourier transform and using that as the new initial condition. Depolarization noise, or the model used in real quantum computers like IBM or Google, is where the state on the Bloch sphere is smeared around the sphere by a factor of the Pauli matrices. And finally, dephasing noise, or the model for noise in open quantum systems, shrinks the state into the Bloch sphere, or essentially the state loses information. In conclusion, introducing noise gives the QEB a lifetime, but emergent phenomena persist. QEBs exhibit robustness and complexity according to our measures, and they should be tested on an experimental platform. Finally, I'd like to thank the people who got me to where I am today, Dr. Lincoln Carr and PhD students Matthew Jones and Mina Fasihi. Thank you for your attention.